let's get started. Those of you that are settling in, just let's try to find a seat and get going. So first couple of announcements. So I think this is the first time they're doing it this week, as on Valentine's Day, which is Thursday. The NSM is organizing a research lab crawl, I guess it's called, where essentially, a lot of you guys are early, first, second year students, and if you want to get, especially for those students, want to learn about some of the research that's going on in the college and potentially opportunities for you as a student to get involved. They have an event starting here at 1 p.m. on Thursday, where you can go around and just tour different research labs. There's going to be a lot of them available. My lab will be one of the ones that's available on the tour if you're interested in seeing. And you'll just get to go learn a little bit about the research, see some of the lab facilities and things, and try to spark some of your interest in getting that as part of your undergraduate education. So that sounds like a very good event. It's the first time they've done it, I believe, so we'll see how it goes. But I think I encourage a lot of you to participate in that. And then one of the other many pre-medical societies also asked me to spread the word about their second meeting, which is this week, Wednesday evening. So the time and location information is in there. So again, if you're interested in HOSA, Health Occupation Society of America, I think it is, check it out. All right, and then a couple other things before we get into the chemistry today. So in a week from today, something happens. I hope you guys remember what that is. That's our first exam starting up, so get excited. Related to that, we're going to have an exam review. I've reminded you about it before, but just to continue to drive this home, we have an exam review. All right. Thank you. We have an exam review Friday of this week. It's going to be 1 p.m. and it's going to be in this same room. And the questions for that, we're going to go over a set of 20 questions that more or less simulate the exam that you'll have the following week. And those should be posted tonight or tomorrow. I just about have them ready. Just didn't get a chance to post them today, but you'll be able to see those in Blackboard. And that'll be good timing because our goal for today is to finish all the material that we will cover on the first exam. So the first exam covers the first 3 chapters, 1, 2, and 3. We're most of the way through chapter 3. We're going to try to get through all of it today, and that way you'll have a whole week to review and prepare for the exam in the various ways that we have to do that. And the exam review will be recorded and posted on YouTube, just like everything else is. So if you cannot come to that on Friday, then you're welcome to check that out online afterwards. All right, so let's first start with, we're going to continue on with Lewis structures. We started this last time. We saw that this is a way of indicating two-dimensional molecular structures. We account for all of the valence electrons in the molecule, and we distribute them as a combination of bonding pairs and non-bonding pairs. And let's first review. We did 3 examples that illustrate various aspects of Lewis structures, and let's go through the first few steps of those last time that we covered before we have to now finish up with some of the key details. Now, I know as we go through this, as I've kind of outlined it, this is probably like a 5 or 6 step process, and you may be thinking, if you've never done this before, that this is a lot of steps. How am I going to remember all this? There's too many things going on here. So this is one of those things, we're going to see this a lot throughout the semester, that I encourage you to just practice it over and over again. The more you do this, these steps are going to come naturally. Some of these steps you're going to be able to do very quickly, in succession, and you're going to start recognizing patterns that are going to help you both do the problems quicker and see when you've done something that looks a little bit weird. So, if you're at the gym getting your gains and doing sets, during your break, draw some Lewis structures and learn how to do this. Or if you're sitting at home and you're texting your crush and you're waiting anxiously for them to reply, do some Lewis structures while you're waiting, and you'll be all set. It's Valentine's Day. What can I say? So it's just one of those things. The more you do it, the more second nature it becomes, and you guys are going to get really good at this. You just have to practice at it. All right, so we're going to quickly go through the first 3 steps that we did last time. All right, so we have to count the valence electrons first. Remember, there's no shortcut around that. If we don't know how many valence electrons our structure has, we're not going to be able to draw it correctly. So let's do the valence electrons for PCl3. We have phosphorus and we have chlorine to consider. All right, and remember that the Lewis structures that we're doing are primarily going to be, or exclusively going to be, from main group elements. So counting their valence electrons is quite simple from the periodic table. So we just look at the group number for those. So we have, in the first example, we had phosphorus and chlorine. Phosphorus is in group 5A, so that means it has 5 valence electrons, and then chlorine is in group 7A, so it'll have 7. So that's how we count valence electrons for main group elements. Just look straight at the group number, and you don't have to think about it any harder than that. So PCl3, we saw we had 1 phosphorus, which contributes 5 electrons. And then remember we have to count for how many of each there are. So for chlorine, there are 3 of them. The formula tells us that. Each one brings in 7 electrons for a total of 21. And so that means, as we already started last time, this structure should have 26 valence electrons total when we're done. NO3 minus, we have nitrogen and 3 oxygens. All right, so finding those on the periodic table, those are, again, these main group elements, group 5 for nitrogen also, and then group 6 for oxygen. So nitrogen will contribute 5 valence electrons. Oxygen, there's 3 of them again, and they'll each contribute 6. So that's 18. But one thing we have to remember is that if we're doing a polyatomic ion, that's going to be a group of covalently bonded atoms that has an overall charge associated with it. Here we have a -1 charge. We have to account for that when we're counting valence electrons. So negative charges add additional ones, positive charges you would take some away. So this minus charge is going to give us 1 more electron for a total of 24. All right, so that's going to have 24 electrons in the structure. And then IF5, I won't scroll back to the periodic table, but those are both group 7 elements, both halogen elements, as you're likely already aware. And so we have 1 iodine that's going to bring in 7 electrons. And even though the valence subshells are different for these, they're still the same number of electrons. So fluorine is also in group 7, so it's going to contribute 5 each. So we saw that this structure should have a total of 42 electrons. So we have to have knowledge about how many electrons there are, because when we're putting them into the structure, we have to be able to count them and make sure we don't put too many or too few. So then the next step, as we saw, was to draw the central atom. Usually the central atom is obvious. It's the one that there's one of, or if there's any doubt, it's the one that's less electronegative, which will sometimes come into play. So for PCl3, very clearly, phosphorus is a central atom. And we start with 3 single bonds to the outer atoms, chlorine. So that's kind of our first starting point. And then remember, from there, we have to start adding in the rest of the electrons. And we first do that by completing the octet of the outer atoms. So with the exception of hydrogen, which of course only forms 1 single bond and just has 2 valence electrons in any sort of Lewis structure, any of these other atoms, when they're on the outside of your structure, should have 8 and exactly 8 electrons. There are going to be very few, if any, exceptions to that. So each of these chlorines should have 8 electrons around it. They have 2 from the bond, so they're each going to get 6 more. So we add those in as lone pairs to start. As we will see, in some cases, we do end up removing some of these lone pairs and making additional bonds, but at the start anyway, we can just put them in as lone pairs. That uses up 24 of our electrons, because now each of these chlorines has 8. 8 times 3 is 24. And so we still have 2 more out of our 26 that we haven't used. And remember, those last ones end up on the central atom also as lone pair electrons. All right? So whenever you have extra ones beyond the octets of your outer atoms, those end up on the central atom. NO3 minus, similar story. We start with nitrogen in the center. We start with 3 single bonds to oxygen. We complete the octets of the oxygen atoms. So we put 6 more on each oxygen to give them a complete octet. And then when we take stock of what we've done so far, we've used 24 electrons up because we have 3 octets, so we have no more left. There's only 24 electrons total in this structure. So in this case, we don't put any lone pairs on the central atom. As I said, we're not necessarily done with these structures. We have a couple other steps we're going to go through today. But this is where we stopped last time, just putting in all of the valence electrons. And then for IF5, what we saw was, again, starting with single bonds to all 5 of our outer fluorine atoms, complete their octets with 6 more. Continue unlocking our achievement of counting by 8, and we find that we have 5 groups of 8 electrons in this structure right now, which is a total of 40. We had 42 that we should have in total. So again, those 2 extra electrons end up on the central atom once we've completed the octet of all the outer atoms. So this is where we stopped last time. We went through, we added all the valence electrons. We started with just single bonds and non-bonding electrons. What we're going to finish with today is evaluating whether we need to include any multiple bonds in the structures, double bonds, triple bonds. We said that those are all possibilities last time. So how do we know if that's the case? The first thing we want to look at then is the octet of the central atom. So sort of the next step in our structure is if the central atom does not have a complete octet, we're going to form one or more multiple bonds. Now the only place that this applies is in NO3- for these three. So if we go back to the structures quickly, we'll see that from the standpoint of the central atom, this phosphorus here has 2, 4, 6, 8. Remember when we're counting octets, we count each bonding pair as 2 electrons, and then each non-bonding pair also 2. So this phosphorus has 8 electrons surrounding it, 6 from the bonds, and then 2 more from the lone pair. So that already has a complete octet, so that's satisfied from that standpoint. But if we look at this nitrogen here in nitrate, right now it only has 3 bonds, and that's only 6 electrons total. So this nitrogen is devoid of its octet. It's a little bit short of the octet. It only has 6. Remember that there are a few elements that do that, boron being the most common, that will frequently have only 6 valence electrons, but nitrogen should have a complete octet, and in this structure it doesn't. So there's some things we're going to have to do. Iodine here in the central atom, we have 2, 4, 6, 8, 10, a total of 12 valence electrons, 5 bonds in a lone pair. That's more than 8, and as we said, sometimes that's going to happen with your central atom. So that's what's called hypervalency. Terminology is not important, but if you have a central atom that is in the third row of the periodic table or below that, it is possible to have more than 8 electrons. In this case, we have no choice. So the only one that really violates the octet rule is going to be the central atom in nitrate NO3-. When we draw that structure, and I should have also put the charge in. I left that out in the last one, so I'll put it here. Remember, this is overall negative charge. So for being rigorous, we should include the negative charge for the whole thing as part of this. Being a little sloppy with my dots, hang on. All right, so this has a negative charge, which is important to keep in mind and indicate with that little bracket. So we saw that when we counted valence electrons, this central nitrogen only has 6. So the way that we deal with this then is we can't add more electrons to the structure. We've already put all 24 valence electrons in. So what we do is we make a multiple bond. We're going to remove one of the lone pair electrons from the oxygen, from one of the outer atoms, and we're going to turn that into a multiple bond, make it a double bond. All right, so it doesn't really matter which one we pick. We're going to get into some more details about this later on about whether it matters which one we pick. But let's take this lone pair, and instead of making it a non-bonding pair on oxygen, let's turn it into a shared electron pair, another bond between nitrogen and oxygen. So all we do then is just turn one of those into a double bond. Again, we still have to have the same number of total electrons, so we don't just randomly draw a bond, and we have to remove one of the lone pairs from oxygen and make that into a double bond. So this oxygen still has its complete octet and no more than 8 electrons around it. We leave the other 2 untouched for now. So the octet rule is the most important rule to try to follow when drawing Lewis structures, notwithstanding the few exceptions to it that do exist. And in this case, by doing this one double bond here, we are able to now have a complete octet on all the atoms. So nitrogen now has a total of 4 bonds, 2 single bonds, 1 double bond, and now it has 8 electrons around it, 2 from each bond. This oxygen still maintains its octet. It has now 2 bonds for a total of 4, and 4 non-bonding electrons, still keeps a total of 8. So we're not changing the octet rule from the standpoint of the outer atoms, but now we have completed the octet of the central atom, so we're good to go in that respect. All right, so that's kind of another step that sometimes comes into play. We saw that it doesn't matter for the other 2 structures we did, the PCl3 and IF5. Those ones, the octet rule was already satisfied. But in this case, we had to draw one double bond to satisfy the octet rule. And then typically the final step we go through then is to determine and evaluate the formal charges. Okay, so formal charges is something where, if we want to make sure that our Lewis structure is as accurate as possible, and again, are there other places where we need to draw double, triple bonds, etc., it's important to also evaluate the formal charges. So we're going to first give you sort of the textbook definition of formal charge, and then we're going to calculate formal charges for all of those structures we just drew. So the definition of formal charge is it's the charge that an atom would have and it's sort of taking the convention that the bonding electrons are shared equally. Now we know this is not really true in many molecules that have polar bonds. We talked about polarity a little bit earlier. But the formal charge definition is a formality, as the name implies. It assumes that the bonding pairs are shared equally between the 2 bonded atoms. All right, so it's saying that the bonding electrons are shared equally, and then you figure out what's the then net charge of that atom in that situation. We'll see how we calculate it here in a second. One thing that should also always be true, and it's helpful to evaluate if you've got your formal charges correctly, is that the sum of the formal charges, so remember that Greek letter sigma, which means sum, the sum of the formal charges should equal the total charge of the molecule or ion. So if it's a neutral molecule, the sum of the formal charges would be 0. If it's a polyatomic ion, the sum of the formal charges would be whatever the overall charge is, be it positive or negative. So that has to always be true. And then how do we calculate it? So the formal charge on an atom, so we're going to calculate formal charge for every atom in the structure. Each one is going to have its own formal charge associated with it. And what you do is you start with the number of valence electrons that atom has. So at the very beginning of drawing a Lewis structure, we always count valence electrons, and each atom contributes a certain number. So you start with this number here, which is the number of valence electrons that atom has by itself. We subtract the number of bonds that it has, or in some sources you will see this as 1/2 times the number of bonding electrons. And this is sort of, again, showing us that we assume that the bonding electrons are shared equally. So if you have a bond between two atoms, we're assuming in this formalism that one of the electrons goes to one atom, one of the electrons goes to the other. So you count one of those two bonding electrons as belonging to that individual atom that you're evaluating. And then we subtract from that the number of non-bonding electrons in total. So we don't have these or do anything to them. The non-bonding electrons we assume belong exclusively to that atom in the structure. So we're not doing a sharing of those as we talked about. So this is how you calculate formal charge. And again, it's one of those things where, brute force memorization of the formula is probably not the best way to do it. Just practice it enough times and it'll become second nature. Now, why do we care about formal charges and how do we use them when we're drawing Lewis structures? So there's two things that we want to keep in mind about this. So what we're typically going to be trying to do is minimize formal charges. So we don't want to have a structure drawn that has a ton of formal charges if it's an avoidable situation. So ideally speaking, this is not always going to be the case, but in almost every case, a neutral molecule should have 0 formal charges, so no formal charges on any of the atoms. So if we have a neutral molecule, uncharged species, it should have 0 formal charges overall. Not only the sum being 0, but also just none, period. So in most Lewis structures for neutral molecules, you will have every single atom, sorry, dropped my pen. A little bit ham-handed today. All right, so every single atom in the structure, typically speaking, for a neutral molecule will have a 0 formal charge. There are exceptions to this. There's exceptions to everything that I tell you about, but there aren't many for this one, especially that you guys will see in this course. A neutral molecule should have 0 formal charges. Now, if you have a polyatomic ion, you have no choice but to have formal charges. So you're going to, your overall ion has a charge associated with it. We said that the sum of the formal charges must equal that. So it's impossible for all of them to be 0. So you're going to have a formal charge somewhere or another. But you still want to minimize the number of formal charges that you have, so the number of atoms that have a formal charge. And you want to minimize their magnitude. Now, again, I hesitate to give hard and fast rules like this because some smart aleck will find an exception to it. But I do think it's pretty safe for me to say that when you're drawing Lewis structures in this course, if you have a formal charge involved, it should be either +1 or -1 only. If you have a +2 or -2 or a +3 or -3 formal charge, assuming you calculated it correctly, there is going to be something wrong with your structure for you to get that, okay? So maybe you'll sometimes start with that, but you should be able to deal with that. Your final structure, the one that has the minimized formal charges, should at worst have +1 and -1, and it's hard for me off the top of my head to think of any exceptions to that you're likely to come across in this class anyway. Okay, so that's something to keep in mind. You want to minimize formal charges. Now, how do we do that? So the first situation you often see is, especially if you're drawing neutral molecules and the first structure that you put down has formal charges in it, if you have a positive and negative formal charge next to each other, we can sort of cancel those out by drawing another multiple bond between those two atoms. So if you have a positive and negative formal charge on adjacent atoms, two that are bonded to each other, you can cancel these out by making a double bond. All right, and as we'll see when we do this once or twice today, you take a lone pair off of the atom that's negatively formal charged and you turn that into another double bond. So you basically remove a pair from the negative formal charge and turn it into a shared electron pair, and that will cancel out that positive and negative. Now keep in mind though, when we're doing all this, that much more important than formal charges is the octet rule. So if we want to assign some sort of hierarchy to this, the octet rule reigns supreme, meaning that you can only exceed the octet if the central atom atomic number is greater than 10. So in other words, those third row elements or below. So if your central atom is in the first two rows of the periodic table, there's a lot of structures we'll draw that have 2p elements at the center, the second row elements. Those you cannot exceed the octet in the central atom. So even if you have formal charges in those structures, if you've already got 8 electrons on your central atom, you have to stop. There's no choice there. And those might be the occasional situations where you might have beyond plus and minus 1 formal charges, but even still, you're rarely going to see that. All right, so that's kind of in abstract what we want to do with these. Let's again look at it now for the structures that we're working on. Calculate the formal charges, see if there's anything we can do to minimize them. So I've just drawn them here again, so I didn't have to hand draw them once again. So we're going to do formal charges for every atom in the structure. So for the central atom phosphorus, remember that what we start with when we're calculating formal charges is the number of valence electrons that atom has by itself. When we counted valence electrons at the very beginning, we saw that phosphorus contributes 5. So this number here, the number of electrons that atom contributes as valence electrons to the structure, is what we start with when we're calculating formal charges. And what we're really asking when we're calculating formal charges is how many electrons does that atom have either in excess or in deficiency of that valence electron amount that it has as a free atom. That's really what we're saying here. So we start with 5 valence electrons for phosphorus. Remember, the first thing we subtract from that number is the number of bonds. So how many bonds does phosphorus have? 3 bonds. And then how many non-bonding electrons does it have total? 2. Remember, we count each of these individually because they both belong to the phosphorus, if you want to think about it that way. So for calculating formal charge of phosphorus, it's 5 minus 3 minus 2, which is 0. Okay? So that has 0 formal charge. And then if we look at the chlorines, each chlorine is going to have a formal charge, but we should notice that they're all identical to each other. Every chlorine has 1 single bond and 6 lone pair electrons. So we don't have to calculate it for all 3 of them separately. They're all going to be the same. So if we do it for chlorine, we saw that the number of valence electrons for chlorine when we counted was 7. It's in group 7 on the periodic table. How many bonds does each chlorine have? Not total, but each one. 1 bond. And then how many lone pair electrons does each chlorine have? It has 3 pairs, but remember we count those individually, so that's a total of 6. Okay? So 6 total, 3 pairs. And so we do 7 minus 1 minus 6, also 0. So this Lewis structure here has no formal charges anywhere, and that's exactly what we would ideally want for a neutral molecule like PCl3. So this structure is, as far as we can tell, complete. There's nothing else we have to do to this one. We don't have to draw any additional multiple bonds to minimize formal charges. All right, NO3 minus. We have a little bit more complicated situation here. So we can start with the central atom nitrogen. There's only one of those. So nitrogen, as we saw, contributed 5 valence electrons. It's another group 5 element. How many bonds does this nitrogen have? All right, I heard a 3 and I heard a 4. I like 4 better because remember we have to count the double bond as 2. So we count each individual bond. 1, 2, 3, 4 bonds. And then how many lone pair electrons does the central atom have in this structure? All right, good. So we get a +1 formal charge on nitrogen. So we might be onto something here that we have to fix later on, but we have to do all the formal charges before we can figure that out. So for oxygen, we'll notice that we have 2 different types of oxygen atoms in the structure. So here the formal charges for oxygen are not all going to be the same because we have 2 oxygens that have a single bond. We have another oxygen that has a double bond, so we would expect those to likely have different formal charges. So we're going to calculate those 2 separately. What I'm going to do to keep them straight is I'm going to label these 2 with little lowercase a's and this one with B. So oxygen A, as I'll call it, which is the one that has single bonds. These two should be the same as each other. Oxygen contributes 6 valence electrons, is group number 6. How many bonds does each of these bottom ones have? And how many lone pairs do they have? Well, they have 3 pairs or 6 total, right? We count total again. So we have -1 formal charge for those two. So we have positive formal charge on nitrogen, -1 for each of these. And then the last oxygen, which is the double bonded one, which I labeled B, still has 6 valence electrons. It's still oxygen, but now it has how many bonds? 2, because we count the double bond as 2. How many lone pair electrons? So we get a formal charge of 0 for this guy. All right, so that has 0 formal charge. All right, now we see a situation here that I alluded to as being possible where we have a plus and minus formal charge next to each other, but can we draw another double bond in this case? Anybody want to take a vote? Throw your neck out there. All right, I see some people at least shaking their heads, so that's correct. You don't want to draw another double bond because remember that our central atom here is nitrogen. And to remind you, nitrogen is in the second row of the periodic table, so it cannot go beyond 8 electrons no matter what. So in this structure here, our central atom, by virtue of drawing this one double bond that we have in there, now has 8 electrons total. It has 4 bonds, which is a total of 8 electrons from the standpoint of the octet rule. So we can't add any more double bonds because this central atom will then be forced to go beyond 8 electrons, which it cannot do. So we stop this structure, even though it has some formal charges, even though it's tempting to try to cancel out this plus and minus formal charge by making one more double bond, we can't do it here. Okay, so we stop here. This is as good as we can do for this structure, even though there are a few formal charges in there. All right, finally, the last one, IF5. Calculate formal charges for this one. These are both group 7 elements. All of the outer atoms are identical, so we don't have to calculate it once. So for the central atom iodine, group 7, it has 7 valence electrons by itself. How many bonds does the central atom have? 5 bonds. And how many lone pair electrons, non-bonding electrons? Okay, so that has 0 formal charge, 7 minus 5 minus 2. For the fluorines on the outside, they have 7 valence electrons also. Each one of those now only has 1 bond. They each have just 1 single bond, but they also each have 6 non-bonding electrons. So those will also have formal charges of 0. So different combinations of bonding and non-bonding electrons, but they both lead to 0 formal charges. This is a neutral molecule, so we're good to go. So from the standpoint of formal charges, there's nothing else we have to do to these molecules here, but it is important to at least keep that in mind for a lot of these structures. All right, so then one last thing to get into about NO3 minus. We're going to talk about this in a little bit more detail in the next chapter. But we have this situation which is called resonance in NO3 minus. So you might have noticed that we have one double bond in nitrogen, and I arbitrarily chose to put it on this nitrogen-oxygen pair. But why did I not put it between this nitrogen and oxygen? Why did I not put it between this one? The reality is it doesn't really matter which one we pick. And so in many situations when the central atom has multiple bonds, which we do in this case, it is sometimes possible to arrange those multiple bonds in different ways that give you equivalent structures. Okay, so there's structures that have the same formal charges. They all obey the octet rule and all that stuff, but the double bond or multiple bonds, whatever the case is, are moved around in different ways. So when the central atom has multiple bonds, we'll see that it is sometimes possible to arrange those multiple bonds in different ways. All right, so we started, as I said, with the double bond drawn up here. But it would have been an equivalent structure if we had instead drew the double bond, let's say, between this nitrogen and that oxygen. Okay, so an equivalent structure that has the same formal charges, same number of electrons, still follows the octet rule, all that good stuff, would be this one here. And we draw the little double-headed arrow to indicate that these are two resonant structures. So they're the same molecule, just two different ways of depicting it that are equivalent. And then the last resonant structure would be the one that has the nitrogen-oxygen double bond in the third position that we haven't drawn it in yet, which as I've oriented this to the bottom right. So this, again, is an equivalent structure, one double bond, two single bonds, same formal charge arrangement, and so on. All right, so these are what are called the three resonance forms of nitrate, NO3-. So they're all equivalent structures, but really all of them have to be drawn to accurately represent the structure of this molecule. So the reality of the situation is, how do we think about resonance? The simple way of thinking about it, which is not entirely correct, is that, we have this one double bond that just moves around between all the three positions. It's not quite like that. We have what's called delocalization, which we will talk about more in Chapter 4. So if you really want to draw the real structure of NO3-, it's not that you have two single bonds and one double bond. It's that you have three identical bonds that are in between the single and double bond. And there's really no good way for us to draw that on paper. So what you will sometimes see if we're trying to indicate these structures that have resonance, where you have, again, in between a single and double bond for each one, you have nitrogen with three oxygens. And then sometimes what people do to indicate that there's this one sort of bond that delocalizes amongst all the positions and gives us bond orders in between 1 and 2 is they'll draw little dotted lines sort of in between each one, like this. Now, the reality of the situation is if a chemist draws a bunch of dotted lines on something, that means they really have no idea what they're talking about or don't really have a good way of indicating it otherwise. So it's not a real perfect way to do it, but it indicates that, again, there's this one bond in this picture that's actually delocalized amongst all the positions, doesn't just stay stationary in one place. So it's hard to draw that and hard to depict that, I suppose. But what we're going to start thinking about is that these three structures indicate that we don't have two single bonds and a double bond, but rather that we have three identical bonds that are in between single and double. And if we want to calculate what that bond order is between single and double, it's pretty simple to do. So the bond order for this nitrogen-oxygen bonds and all in these structures would be, how many total bonds do we have between nitrogen and oxygen throughout the whole structure? 4. There's two singles and a double in each of these resonance forms. So there's a total of 4 bonds, but they're distributed over 3 NO bond vectors, right, or three positions. So there's a total of 4 bonds distributed evenly over the 3 nitrogen-oxygen pairs, and so the bond order would be 4 over 3, or 1 1/3. So again, indicating that it's between a single and a double bond. We saw that, for most structures, the bond order is either clearly an integer number, 1, 2, 3, indicating how many shared electron pairs there are. But in resonance structures like this, the real bond order is somewhere in between single and double, or double and triple, whatever the situation is. All right, so those are some things we'll come back to a little bit later on when we start talking about bonding in more detail. But suffice it to say, when you draw Lewis structures, if you have this situation that'll come up sometimes, you have to be able to draw Lewis structures that are shown as resonance forms and be able to evaluate those as well. All right. So the other time that we sometimes use formal charges is to expand the octet of the central atom. So formal charges, we don't necessarily just have to cancel out positive and negative formal charges or complete octet rules. There are other situations where formal charges come into play. Now, this sometimes occurs when our central atom has the ability to go beyond 8 electrons. So if we draw SO3, our central atom is sulfur, which is in the 3rd row of the periodic table. And so we could, in principle, go beyond the octet rule for the central atom. Now, if we're being totally honest with you, there's a little bit of controversy about whether this actually happens or not. Do the central atoms actually expand their octet ever? We kind of tell you that they do, but in some sense that's a lie. If you do more high-level analysis of the central atoms, they don't really go beyond the octet rule. So typically the way we'll do this on homework problems and test questions is if we have a Lewis structure where it is possible to expand the octet on the central atom, and we want to ask you some question about that, like bond order or number of double bonds or formal charges, whatever the case is, we will specify that you either need to obey the octet rule for that structure or minimize formal charges. So that's going to dictate how you actually draw that structure and what structure you actually evaluate. Okay, so for example, for SO3 is one of these classic cases where we could expand the octet on the central atom. And so one way we could ask a question is draw the Lewis structure for SO3 that follows the octet rule. So if we're going to do that, then we have to count electrons, sulfur and oxygen. Okay, so sulfur and oxygen are both group 6 elements, so they're each going to contribute 6 valence electrons. So the starting steps are all the same. We don't really have to worry about this octet rule thing until closer to the end. So we have 6 electrons from sulfur, and we have 3 oxygens, each with 6 electrons, so another 18. So this structure should have 24 valence electrons. So if we want to draw the structure that follows the octet rule, we still start with the same series of steps. Sulfur at the center, 3 single bonds to oxygen. We complete the octets of the outer atoms. And so how many electrons have we used? We've used 3 sets of 8, so that's all 24. So this structure will not have any lone pairs on the central atom. Once we complete the octets of the outer atoms, we've used them up. But in this current structure, does the central atom have its octet rule completed? No, because this still, again, like nitrate, NO3- only has 3 bonds. So right now, this central atom only has 6 electrons, fewer than 8. So if we want to draw a Lewis structure that follows the octet rule, we have to complete the octet of the central atom by adding 1 double bond. So again, we take off a lone pair, any of the 3, and we draw a double bond. And that's going to be the structure then. And now each of these atoms in the structure has exactly 8 electrons. So if we were asking you to draw a Lewis structure that follows the octet rule, we would stop here, because we don't want to expand the octet on anything if we're trying to follow the octet rule. We will specify that in most of the questions where that comes up if there's any ambiguity. So we stop here, and then whatever we ask you about this structure, let's say the question was how many resonance forms are there. So just like we saw for NO3-, this structure that follows the octet rule will also have 2 additional resonance forms, because we could have drawn that 1 double bond in any of those 3 places. And I already did that wrong. I drew the same one again. So we would put the double bond in one other place. And then we would draw, running out of room, but we put the double bond in the last position down here. So again, this structure that obeys the octet rule has 3 equivalent Lewis structures that are called resonance forms. But it obeys the octet rule because none of the atoms in the structure have anything more than 8 electrons or anything less than 8 electrons. They all have exactly 8 electrons. So that's one way we could ask questions about structures like this. But then in some cases, what we will do is we will say, draw the Lewis structure for SO3 that minimizes formal charges. So when we get to this picture that we had, which follows the octet rule. So the octet rule is more or less non-negotiable, with the exception of a few elements like boron that have fewer than 8 electrons or hydrogen. You typically want to follow the octet rule, so that's never going to be left aside. But once we get to that point, as we did here, sometimes we will say, okay, well, now draw the structure that minimizes formal charges. And we see that sulfur, again, is in the 3rd row of the periodic table, so it is possible for that central atom to have more than 8 electrons. It is okay for us to do that if we specify that we want you to minimize formal charge. So let's see what the formal charges are in this situation. So similar to the nitrate structure, we have a central atom, and we have, again, 2 types of oxygens, one that has single bonds, one that has a double bond. We're going to start noticing some patterns here. Let's start with sulfur first. This one's a little bit different than before. So sulfur contributed 6 valence electrons, and what we have to subtract is the number of bonds. So in this structure here, sulfur has 4 bonds, and it has 0 non-bonding electrons. Okay? So right now our sulfur has a +2 formal charge. I told you that normally that's bad. In this situation, if we're following the octet rule, we have no choice but to do that. We can't, we can't do anything other than this with the octet rule followed. But if you look at it in the oxygen atoms, you have, again, A and B, 2 different types of oxygen. Same pattern as before. These oxygens have 1 single bond and 6 non-bonding electrons. So 6 is the number of valence electrons, 1 bond, 6 non-bonding electrons. So these are each -1, the ones that have single bonds. That's a pattern you'll see a lot. Oxygen with a single bond and 6 non-bonding electrons has a -1 formal charge. All right, and then the second oxygen atom here, which has the double bond we saw before, 6 valence electrons, 2 bonds, 4 non-bonding electrons, 0 formal charge. Okay, so that one's fine. But if we're asked to draw the Lewis structure that minimizes formal charge, we should recognize that this isn't it, okay? Because we have a +2, we have 2 -1s. They add up to be 0, which is good, but they should be ideally not there at all. So our central atom can expand the octet, and as we saw, if you have a plus and a negative formal charge next to each other, you can cancel those out by drawing one more double bond. So if we have a plus 2 and 2 minus 1s, we can get rid of all the formal charges by making 2 more double bonds, one to each oxygen. So we're going to take a lone pair off of this oxygen and make another double bond, a lone pair off of that oxygen and make another double bond to give us this structure here. So we've removed one lone pair from each of those, so now they each have just 4 non-bonding electrons left. And now all 3 oxygens are equivalent to each other. So still the same number of electrons. We took 2 from here and made a new bond. Took 2 from here and made a new bond. Our central atom now has beyond 8 electrons because it has, again, 2, 4, 6, 8, 10, 12. 6 bonds total, 12 electrons. But because the central atom is in the third row of the periodic table, it is acceptable to do that in some formalisms. So this would be the structure that minimizes formal charge. If we calculate the formal charges for all of these, they're going to be 0. So we'll verify that here in a second. So this has 0 formal charges. Let's see if that's true. But we did, again, cancel out 2 because we made 2 more double bonds, cancel out a plus 2 and 2 minus 1s. Sulfur in this structure now has valence electrons of 6 and now has 6 bonds. Still 0 lone pairs. We can't just pull electrons out of thin air, but now the formal charge is 0. And then oxygen here has still valence number of 6 and 2 bonds, 4 non-bonding electrons, same as OB over here, 0 formal charge. So now all 4 of these atoms have 0 formal charges. The oxygens are all equivalent. The central atom has 0 formal charge. And this would then be the Lewis structure of SO3 that minimizes formal charge. So be careful on the homework assignments. Look at what we specify. For some of the structures, we will specify to either obey the octet rule, in which case no atom in the structure should have more than 8 electrons, or we will specify to minimize formal charges, which means, especially for neutral molecules, you should try your best to get to a situation like this where you have no formal charges on any of the atoms. All right, so any questions on that? All right, so now let's move on to the next topic, which is, well, let's do one more question on resonance structures just to see how this works. Okay, so the first thing we'll have questions like this. We're going to give you a bunch of potential resonance forms. This is for ClO3 minus, which, as we'll see later on, is called the chlorate anion, the polyatomic anion. And we want to know which of the following is the most important resonance contributor for ClO3 minus. So when we're evaluating resonance contributors, there's 3 things we have to evaluate to decide which one is the most important. You know, that's, again, a qualitative term, but when we draw potential resonance structures, the one thing that they have to have correct is the number of electrons. All right? So anything that would be considered a resonance structure has to have the correct number of valence electrons. If it doesn't, it's not the correct structure at all, so you don't even have to evaluate it any further than that. So we first need to figure out, in ClO3 minus, how many valence electrons should we have? All right, so Cl has, it's group 7, so it's going to contribute 7 valence electrons. If you have the periodic table in front of you, you can find it. Oxygen, as we just saw, has 6 valence electrons, and there's 3 of them. And then we have, again, this negative charge. Don't forget about the minus charge. So we have 1 more valence electron to add from the negative charge. So any resonance structure that we draw, whether it be a good one or a bad one, should at least at the minimum have 26 valence electrons. If it doesn't, it's not a resonance structure. So that's always the first thing to check. We might be able to eliminate 1 or more of these just on the basis of valence electrons. If we look at these 4 structures, choice A here has 8, 8, 8 is 24 plus 2 is 26. 3 octets plus the 2, so that one's good. This one has, again, 3 octets on the oxygens, another 2 on the central atom, so that's 26. So choice C, 8, 8, 8, and then 2 more is 26. But if we look at choice D here, we have the octets from the oxygens. 3 8s is 24, but then our central atom just has 1 additional non-bonding electron. Now, it's not impossible to have a single non-bonding electron like that, but that's not the right number of electrons for this structure. So this structure can't be a resonance structure because it has only 25 valence electrons. It needs to have 26 for it to be considered. So that one we've eliminated on the basis of the number of electrons. So that's always the first easy thing to check. The next thing we want to check is the octet rule. Now we're not specifying here that they have to obey the octet rule. Our central atom does have more than, it's in the third row of the periodic table, it has atomic number greater than 10, so our central atom could have more than 8, and that's okay. But let's evaluate whether any of these violate the octet rule. So if any of these structures do not follow the octet rule, especially for the outer atoms, we can eliminate them right away. So if we look at this structure, all of the atoms, the oxygens have octets. The central atom has 2, 4, 6, 8, more than 8, so that's okay. This structure here, octets in all the oxygens, 2, 4, 6, 8, 10, 12 on the central atom. Structure C, 2, 4, 6, 8, 10, 12 also. Or no, sorry, 14 octets in all the outer atoms. So all of these structures have exactly 8 electrons on oxygen, which is what they should have. They have more than 8 on the central atom, which is okay for chlorine. So these are all in compliance. So none of these violate the octet rule. So the only thing that we can evaluate now are formal charges. So the last thing we look at, this is sort of the hierarchy of things we should look at in this order, is formal charge. To figure out which of these resonance forms is the most likely. Now I'm not going to go through all of these in detail because it'll take a long time, but you can verify these on your own. So in this structure A here, the oxygen, we've seen these patterns multiple times already. If you have an oxygen with a single bond and 6 non-bonding electrons, those are -1. So, and then this one is 0 with the double bond. And then we calculate the formal charge for the central atom. 7 valence electrons from chlorine. We subtract the number of bonds, which is 4. 7 minus 4 minus 2 is +1, right? Did I do that right? 7 minus 4 minus 2 is +1. Yes, we can do math today. All right, good. So those are the formal charges in that structure. +1 on the central atom, -1s on the outside. +1 and -1s aren't bad, but we should recognize the possibility of being able to maybe cancel one of those out by drawing another double bond. Let's look at choice B, and that's exactly what we've done in B. We've drawn one more double bond. So in choice B, we have a 0 formal charge on both of these oxygens that have double bonds. We still have one singly bonded oxygen, which, as we've seen many times, gives you -1 formal charge. And then the central atom in this case is going to be 7 for the valence electrons. Now we have 5 bonds, 1, 2, 3, 4, 5. 7 minus 5 minus still 2 lone pair electrons. 7 minus 5 minus 2 is 0. Remember, the sum of the formal charges should equal the total charge. So these should all equal -1 when we add them together. +1, -1, -1, just the 1 minus 1. All right, choice C here. We've gotten rid of all of the formal charges on oxygen. All of the oxygens now have double bonds with 4 lone pair electrons. So we have 0 formal charge on oxygen, and then the chlorine atom has 7 minus 6 bonds -2. 7 minus 6 minus 2 is -1. So in this case, we've put the negative formal charge on the central atom. Okay? So looking at choice B and C, which of these do we think is better? They both only have a single formal charge that minimizes the number of formal charges, but is it better to have the negative formal charge on the outer atom or on the central atom? Anyone want to hazard a guess? I heard a lot of central atoms. Unfortunately, I have to disagree with that. So the reason is, I'll write out the net outcome first. So choice C is the best choice because it has the negative formal charge on the outer atom. It's better to have that situation, and I'll tell you why in a second. And the reason is because it's better to have it on the more electronegative atom. Okay, because remember that electronegativity is a measure of how badly that atom wants electrons when it's covalently bonded to something else. So if it has a higher electronegativity, it would be the one that more wants to bear that net negative charge. Okay? So oxygen is more electronegative than chlorine, so if you have a choice of where to put a negative formal charge, oxygen or chlorine, chlorine should be the one that gets it. So typically speaking, in almost every structure, the more electronegative atoms are on the outside, so that usually means if you have a choice between formal charge on the central atom or the outer atom, if it's a negative formal charge, it should prefer to be on the outer atoms. Okay? All right, so choice B and C both minimize formal charges in that they only have one -1 formal charge, but it's better to have that negative formal charge on the outer atom in this situation. All right, any questions on resonance structures and Lewis structures before we move on to the last topic of Chapter 3? All right, the last topic we're going to cover in Chapter 3 is what's called nomenclature. So this is how to name different kinds of compounds. And again, a big part of this is just learning to speak the language of chemistry. You guys are all, budding chemists trying to become better than I am at chemistry at some point in your life, and you'll get there soon if you study hard. And one of the things you have to be able to do is speak the language. And part of the language of chemistry is nomenclature. How do we name different compounds? And we're going to cover the basics of that in this course. And you'll see a lot more of that if you take organic chemistry. Nomenclature just gets even more ridiculous in that class. So we're going to stick to the basics here. We have 3 categories of compounds we're going to learn how to name. The first one is ionic compounds, and they're going to be relatively simple ionic compounds. So as we talked about in very basic detail earlier on, an ionic compound includes a metal and a nonmetal paired together. The metal bears a positive charge as a cation. The nonmetal gains electrons, becomes an anion. So that's what we want to recognize as being an ionic compound. It's a combination of a metal with a nonmetal. Now, how do we name those? So the order for the name is that we put the metal first, which is our cation. So in the name of any ionic compound, the metal should come first, and the nonmetal comes second. That's going to be our anion. And this order applies to both the formula and the name. So by convention, when we write the formulas for ionic compounds, we put the metal first and the nonmetal second. And when we name them, we also do that same order. Okay? So how do we put these in the name then? We have the 2 separate parts of the name, the cation and the anion, and what happens to them in that. So the cation, we just take the name of the metal. We don't do anything different to it. So if our ionic formula has Na plus as part of the formula, the first part of the name is just going to be sodium. That's just the name of the element. So for the metal part of the formula, we don't put any endings or change anything about the name of the element. It's just the name of the element itself. If we had calcium 2 plus, we would just call that calcium as part of the name of that compound, and so on. So the metal part, we don't change anything. The anion, though, we do things a little bit different. We take the root name of the anion, but we change the ending to be IDE. So IDE is one way we indicate that something has a negative charge, although it's not exclusive to that. And so we change the ending of the anion to be IDE from whatever the name of the element is. So if you have F minus in your structure, that's fluorine. The element is fluorine, but you change the INE to an IDE. So this would become fluoride. All right. So fluoride would be the name of the anion. If we have O2 minus, that's oxygen. We change it to oxide. So some of the names get clipped a little bit more than others. So some of them you should become familiar with. And then same with N3 minus. We don't call it nitrogide. We call it just nitride. All right. Again, we're not going to have you type too many names, I don't think, in problems. So as long as you can recognize them, whether you can spell them exactly correctly or if you forget little details. The types of questions we ask is probably not going to be a big deal. But be familiar. There are tables in your books, and I reproduced them at the end of here, that have all these common anions in them. Most of them you don't have to memorize for these simple ones because we know from the periodic table how to predict what charge something is going to have. We talked about that last week. And you just have to put the IDE ending on, so there's not like all these differences between them. It's pretty conventional for all of them. And then in the formula, we have subscripts that indicate how many of each ion there are. We don't have subscripts in the name, just in the formula. And remember that, as we talked about before already, we want the lowest whole number ratio. Now, the key thing that distinguishes the nomenclature of ionic compounds from covalent compounds, which will make more sense when we talk about covalent compounds later, is that ionic compounds, we don't have any prefixes in the names. So we'll see for covalent compounds, we use prefixes to indicate how many of each element there is in the formula. We don't do that for ionic compounds because the charge of the ion will automatically tell us how many of them there are. Okay? Because we know how to predict the charges of ions in the periodic table, they have to occur in a ratio that balances the charge, so it would be redundant to have those prefixes in the name to indicate how many there are because it comes straight from the formula or from the charges of the ions and then the formula. So you don't have any prefixes in ionic compounds. It's just metal, nonmetal, and that's it, okay? So here's a few simple examples. If we have MgCl2, now remember we expect you to know the names and symbols for the first 36 elements, not necessarily the order they come in, but you have to know which symbol goes with which name. So Mg is magnesium, And if we go to the periodic table, if we want to review what the charges are, magnesium is a group 2 element, so it would be a 2 plus cation. So if we're writing the formula for this compound, it's MgCl2 because we have Mg2 plus, and then our chlorine is in group 7 here, so that would acquire 1 extra electron to get noble gas. So that's going to be a 1 minus anion. We already talked about this stuff before, and we have 2 of those. But again, those formulas don't really transfer to the name. So we name the cation as just the metal. Mg2 plus is just named as magnesium. Sorry, I already spelled that wrong. And then we have Cl minus is chloride. And then finally we have this next one here. This one I shouldn't have given you because cesium is beyond atomic number 36. But if it was multiple choice, that should be pretty obvious. So cesium is, Cs is cesium, and again we just name the metal as is. Remember that O2 minus is what we call oxide. So this would just be cesium oxide. All right, so once you know the names of the anion, cation, anion, you just stitch them together for the ionic compound. It's as simple as that. A couple other examples give the name and formula now for the ionic compound that's formed from strontium and iodine. Strontium, I think I also messed up here. This one is, beyond 36, so we'd have to give you that symbol. But the symbol for strontium is Sr. You wouldn't have to memorize that, but it's Sr. It's in group 2 of the periodic table. So what's the charge of the cation going to be? Plus 2. And then we just saw chloride. Iodide is right below that. It's also in group 7. So that's going to be minus 1. We said last time that the dummy way to get the formula is just to take the charges and make them into subscripts on the opposite ion. So we're going to end up with SRI2 to balance the charges. So that's the formula. And then the name, again, it doesn't matter what the ratio of them is. The name is just the name of the 2 pieces. Strontium. And then we have to change the ending from Ne to IDE to make it an ionic compound. Strontium iodide. Okay, simple as that. And then finally, sodium and sulfur. Sodium we should know is Na, sulfur is S. These ones you are expected to know. Find them on the periodic table to get the charges. Sodium we should know by now is in group 1, forms plus 1 cations. Sulfur is in group 6, the oxygen group, so it's going to gain 2 electrons to form a minus 2 anion to get to the noble gas configuration. So the charges of our ions are Na plus and S2 minus. This is all review. To get the formula, we just, again, simple way to do it is just to cross the superscripts and make them subscripts. And that gives us Na2S to balance the charges. That's the formula. And the name is just sodium. And then we put sulfide at IDE ending. Exactly. Okay? So that's how we do simple, these are called binary ionic compounds. So these are ones that just have 2 elements in them, relatively simple. All right, there's a little bit that comes into play if we deal with transition metals. So transition metals are those ones in the middle part of the periodic table. We cannot easily predict what charges they have, and many transition metals have multiple possibilities for the stable cations that they can form, so you have to indicate that in the name. So the rules for ionic compounds are very similar, I would say. The formula has the exact same convention. You just put the metal first and the nonmetal second, nothing else. Cation, then anion. But the name is where things are a little bit different. So the difference in the name is that the first part of the name, which is the metal, is going to include a Roman numeral that tells you what the charge of the metal is. The reason we do that for transition metals is, again, because transition metals have the possibility of forming more than one different cation. So it's not obvious from just the name, if we didn't include that, what is the charge on the metal in those situations. So there's going to be a Roman numeral in parentheses after the metal that indicates what its charge is. All right, so if our ionic formula has iron Fe3 plus in it as the metal, that would go into the name as iron with a Roman numeral 3 after it. That indicates that it's iron plus 3. If we had Fe2 plus we would put that in as just iron with a Roman numeral 2 after it. Okay? So the Roman numerals in transition metal compounds indicates the charge of the metal. Because if we just had iron and chloride together and we called it iron chloride, you wouldn't know from that name whether it's iron plus 2 or iron plus 3. So for transition metals, you have to indicate the charge. For main group metals, they only have one charge possible. Some main group metals in the P block can form multiple different cations. So for these ones, which we won't see a lot in this class, you do need to indicate the charge of those as well. But mostly it's for transition metals. There are also some common names that are involved in transition metal compounds, which I don't think we're not going to hold you responsible for these, but again, just to help you learn the language of chemistry, and if you're looking through older textbooks especially, they have this. So if you have two different cations for a metal, one that has a higher charge, one that has a lower charge, the higher charge gets an IC suffix, and it usually takes the Latin root name, so it's even more confusing than that. So Fe3 plus is also sometimes referred to as ferric. So ferric chloride would be iron 3 chloride. And then if you have the one that has the lower charge of the two, would get an OUS ending. So if it was an iron 2 compound instead, iron 2 plus, you would call that ferrous. And it uses the Latin name ferrum, which is the name for iron that Fe, the symbol, comes from. So it's a little bit confusing, but you will see that occasionally in other sources. I don't think we're going to hold you responsible for it, but same with copper. You have cuprous and cupric. Now that you know that, you should be able to tell me what this is. It's a Ferris wheel. An inorganic chemist's favorite carnival ride, a Ferris wheel. Good. All right, so that's what we have for, and now there's actually real chemistry researchers that have tried to make Ferris wheels and sell their papers like this. It's hilarious, but if you have that kind of humor. All right, so that's some naming for transition metals. The last thing we have to cover for ionic compounds are what are called polyatomic ions. So these are, we've already drawn the structures of a couple of them. We did NO3 minus, and these are groups of covalently bonded atoms that have an overall charge. And these can also be parts of ionic formulas, so we have to know how to name them and how to use them as well. So they're groups of covalently bonded atoms, and they have an overall positive or negative charge. Most of the polyatomic ions that you'll have to know are negatively charged, but there are at least a couple of positively charged ones. Table 3.7 in the book, which I've reproduced in the notes if you don't have the book, that has the full list that you'll be responsible for. And again, people get a little bit hot and bothered with this, like, oh, I can't believe we have to memorize so many polyatomic ions, but try to think of it as memorization. For example, I've given this analogy to some students before. You guys at the age of 18 to whatever that you guys are, you probably know a lot more words than you did when you were 5. But did you memorize all those words, or did you learn them and internalize them? So that's how you want to treat this kind of vocabulary stuff. Just try to make it part of your everyday vocabulary so you don't even have to think about it. It takes a while to get to that point, but the more you use it, the more you practice it, you'll get there. So when do we use parentheses? So if we have a formula that has polyatomic ions and there's more than one of them in the formula, so there's more than one polyatomic ion in the formula, we have to put them in parentheses to bracket them and indicate that that's a whole charged unit, that they're not just separate atoms. Okay? So if there's more than one polyatomic ion, we put it in parentheses. It will be enclosed in parentheses. And then it'll have a subscript on the outside that tells you how many of that ion there are in the formula. All right? So we do use parentheses sometimes, so don't be confused by that. A couple examples where we do and do not use parentheses. If we form an ionic compound from Na plus sodium and then NO3 minus, which we've already drawn the structure of, which is called nitrate, the formula for this compound is a +1 cation and a -1 anion, so we just need one of each. So you would just write it as NaNO3. It's understood in this case that the NO3 is all together. If you put parentheses around it, I wouldn't technically count it as wrong, but conventionally we don't in this situation if there's only one of them. But if we had calcium pair with nitrate, which is calcium 2 plus, and still NO3 minus, nitrate always has a -1 charge. In this case, we need to, again, swap the subscripts. So we would have to have 2 NO3 minuses to balance the +2 charge. So when we write the formula for this, we would do calcium And then we have NO3 in parentheses, and then we have a 2 on the outside that tells us that we have 2 whole NO3 minuses. So that's how we kind of write these formulas when there are polyatomic ions involved, when there's more than one of them. All right, we don't write it as this. This is confusing. If we try to do it like this without the parentheses, it looks like NO32. Or we don't combine them together. We don't say that it's CaN2O6, even though that is a total formula, because that doesn't clearly indicate that NO3 is together as a whole unit. So both of these are wrong. We don't do that. We have to have them in parentheses. So might be obvious, but just in case you see it and get confused by it, that's what we have. So let's do some examples with transition metals and polyatomic ions, just to get used to this. So if we have Fe2O3 and we want to name it, we have to figure out for transition metals what is the charge on each ion. And that's going to come from the formula in this case. So the formula doesn't tell you the charge directly. So we have 2 irons. We don't know what the charge is for those off the bat, but what's the charge for the oxygen going to always be? Remember from the periodic table, oh no, don't close, minimize. All right, so in the periodic table, oxygen is in group 6, so it's going to form a 2- anion, as we've seen many times today already. So if we have 3 2- anions, that's a total of 6 negative charges. And so what does the positive charge have to be on iron to balance that out? 6 total, but there's 2 of them, so each one's going to be +3. Okay? So the charge on iron is +3. In this case, we have to work a little bit backwards from the formula to figure out the charge. Okay, yes? I guess it works in this case. I don't know if it will work in every case, but I suppose you could reverse that. It won't always give you... The only time it doesn't work, though, is if they're not in the whole smallest ratio. So I wouldn't rely on that, because if we did, for example, calcium oxide and try to do that, you would get that each of these is +1, but they're actually -2. So you have to really figure out the charge on the anion first, which is going to be invariant, and then back out the charge of the metal from that. So in this case, the anion is 2-, there's 3 of them, so we have to have 2 + 3 cations to balance. So we need that for this name because, again, for transition metals, we have to indicate that this is iron 3 now, with parentheses in Roman numerals, and then it's going to still be just oxide. So similar as regular ionic compounds, but the 3 in parentheses tells us that it's iron with a +3 charge. And now we have CuSO4. So likely haven't learned all the polyatomic ions yet, but you will, and you will need to in about a week if you haven't yet. So SO4 is sulfate, which has a 2- charge. So you do need to know the formulas, names, and charges for the polyatomic ions, all 3 of those things together. And so SO4 is sulfate, which has a 2- charge. And so if SO4 has a 2- charge, what does the charge of the metal have to be? And again, this is actually an example where you can't just reverse the subscripts because that would give you the wrong charges because they're, in this case, +2 and -2, still a 1-to-1 ratio. And so when we name this, we would call it copper 2 sulfate, or using the old school nomenclature, we would call it cupric sulfate. So for polyatomic ions, most of them have ATE or ITE endings. You don't change the ending of those. You just use them as is. So for polyatomic ions, you just name the metal cation, name of the anion, done. And don't change any endings in this case, okay? Some other examples, chromium-3 permanganate. In my opinion, going from the name to the formula of a transition metal compound is actually easier because the name will directly tell you what the charge is on the metal. So if this is chromium-3, it's going to be Cr3+. Permanganate, which again is one of the harder ones, is MnO4 with a -1 charge. So that's one of the ones you'll have to learn. And in this case, now that we have the charges, we can follow the little shortcut of crossing the charges and making them the subscripts. So we would have 1 chromium with 3 MnO4 minuses to balance the charge, because each of these is -1, so we need 3 of them to balance the +3. So we have to put that in parentheses, MnO4, put a 3 outside to indicate there are exactly 3 of those to balance the charge on the metal. And then tin-4 chloride. Tin, I think, is beyond 36, so not one you'd have to memorize, but the symbol for tin is SN. It's going to be +4. Or I guess 4+ is how I usually write it, so I won't confuse you there. +4. And then Cl, as we know, is chloride, Cl-. All right, so again, named a formula, we just take the charges as we did before and convert that into a charge balance formula, which becomes SnCl4. All right, so those are the formulas for that one. All right, the last thing we're going to cover in the little bit that we have left are covalent compounds. We're only going to cover one class of covalent compounds, which are called binary covalent compounds. So binary covalent compounds are just two elements, just like the binary ionic compounds are only two elements, and we use prefixes on each element to tell us how many there are. So going from name to formula, formula to name for covalent compounds is in some sense much simpler because we don't have to think about charges, we don't have to think about charge balancing, nothing like that. We just have to know how many of them are in the formula. So if the formula is given to us, that number is already there, and we just translate that to a name or vice versa. So for this, we need prefixes on each of the elements to tell us how many there are. So the prefix for 1 is mono, 2 is di, 3 is tri. So these are, I think, Greek or Latin or both. I don't remember which language they come from, but they're these common prefixes that indicate numbers that you'll likely see in other contexts in your life. And then we have penta, hexa, hepta, octa, nona, and deca. Those are as high as we'll go in this class. All right, so mono, di, tri, tetra, and then I think the last three are pretty easy. Penta, hexa, hepta, octa, nona, deca. If you've ever counted in Greek or Latin before, you'll know that. Okay, so then the mono prefix is only used on the second element in the formula. So if you're naming a compound that has two elements and the first element there's only one of, you typically don't put the mono on it, and if there's no prefix at all, it's assumed to be just one of that element. We'll see a couple examples of that. We've already talked a little bit about, like, let's say carbon dioxide, right? You don't say monocarbon dioxide, you just say carbon dioxide if it has one carbon. So if the first element is only one of them, you don't include mono, but if it's the second element, that one's there. All the rest of these prefixes, you have to have them on both elements whenever they're relevant. All right, so those are the prefixes we need. So for binary covalent compounds, that's when these apply. These are covalent compounds that have two elements only. So it has two and only two different elements in the formula. That's a binary covalent compound. Covalent compound, as a review, means two nonmetals bonded together. Ionic compound is a metal with a nonmetal. Covalent compounds are two nonmetals, so things from the right side of the periodic table combine together to form covalent compounds. Those are the types of compounds we typically draw Lewis structures for, as we started today with. Those are all covalent compounds or polyatomic ions that have covalent bonding. And then the rules for nomenclature, typically the ordering is very obvious. We give you the formula and you name them in the order that they're given in the formula. There is a convention for that, though. So the first name in the formula is the element with the lower group number. So that's the element that's to the left of the other one on the periodic table. So if you have, remember we've talked about carbon-oxygen compounds a lot already. If you have CO, you put it in that order, carbon monoxide, because carbon is to the left of oxygen. You don't call it oxygen monocarbide, you call it carbon monoxide. You put the lower group number first. Carbon is in group 4A, oxygen is in group 6, so that's why carbon comes first in that formula. But again, we'll usually give you the formula correctly, and you just have to name them in the order they're given to you, not worry about this. Now, if they're in the same group, though, if you have a compound with two elements from the same group, so the two elements are in the same column of the periodic table, which sometimes happens, the higher period comes first. So that's going to be, again, the lowest row on the periodic table. So the periods are the rows in the periodic table. So if you have two elements in the same column, the one that's further down the row, or down the column, with a higher period number is the one that comes first. So we again saw the compound with sulfur and oxygen was one of the examples we worked through, and it was sulfur first, then oxygen. The atom that's lower comes first. Sulfur trioxide, not trioxygen sulfide. Okay? So it's the lower period number that comes first in SO3, which is the example we work for, or any other compound like that. And then finally, even though these aren't ionic compounds, we still use the IDE ending only on the second element. All right, so the first element just keeps its name, although it might have a prefix associated with it if there's more than one of it. The second element definitely will have a prefix to indicate how many there are and an IDE ending. All right, and then again, the big difference between ionic compounds is that the prefixes are used. to denote how many of each element there is. And the formula for an ionic compound, for a covalent compound is not going to be reduced to its lowest whole number ratio. And the reason is that for covalent compounds, we're not dealing with charges in this case. And in reality, if you have two different formulas that have the same ratios but different absolute numbers, those could be two entirely different compounds. So for example, NO2 and N2O4, these both have the same ratio of nitrogen to oxygen, 1 to 2, but these are two different compounds. So we wouldn't want to take this formula N2O4 and reduce it to NO2. That makes it totally different. So for covalent compounds, we do not reduce the formulas, because different formulas could be different compounds altogether, or likely are. All right, so those are the big differences between ionic and covalent. Covalent compounds use prefixes, and they don't reduce the formulas to the lowest whole numbers. So let's close with a couple examples of binary ionic compounds. Either I give you the formula and you give the name, or I give you the formula, or I give you the name and you give me the formula. We'll put off acids till next time. So, all right, so last page here. Let's get through this. So if we have SF4, the first element is sulfur. The second element is fluorine, but remember that we changed the ending to IDE still for the second element, sulfur, and then we have to indicate how many there are. Now remember, we don't put mono on the first element, so there's only one sulfur, but we don't include that on the first atom, or the first element in the formula. So this just stays as sulfur, but then we need a prefix to tell us that there are 4 fluorines. The prefix for 4 is tetra. So this SF4 will be named as sulfur tetrafluoride. Okay, it tells us that we have 1 sulfur and 4 fluorines in the formula. In P2O5, again, these are pretty simple, I think, because we just have to take the numbers and translate them into prefixes. So 2 is the prefix that's di, and then 5, the prefix is penta. So we do need a prefix on both in this case because our first element, phosphorus, has more than 1, so we have to tell them how many there is. So it's going to be diphosphorus. We don't change the name otherwise, but we put a prefix to tell us that there's 2, diphosphorus, and then we have pentoxide. One little detail that we're not going to, hold you over the fire about is that if your element begins with a vowel, you often drop the vowel from the prefix. So it wouldn't be pentaoxide, it would just be pentoxide. Again, a small detail that you don't have to drive yourself crazy over, but that's why this is the official correct name, diphosphorus pentoxide. Again, the prefixes tell us how many. Now we're going name to formula. So if we have nitrogen trichloride, nitrogen, the symbol is N, and there's no prefix on the first elements. That means there's 1 of them. Trichloride, Cl is chloride. Tri means 3, so it's NCl3. And then we have disulfur decafluoride. So di, again, means 2 as we saw, so it's going to be S2 for sulfur. Decafluoride, fluoride is F. Deca means 10, so it's going to be S2F10. So I think binary covalent compounds are, in my opinion, the simplest category. We'll finish up the loose ends next time with naming acids, the very last topic in Chapter 3 that we didn't quite get to. Also, one other thing, the homework review today, I screwed up and didn't record sound, so I did it again. It's going to be posted tonight, so sorry about the delay. And we will have, again, finishing up Chapter 3 and getting into Chapter 4 on Wednesday.